Hello everyone. So I'll start this video by summarizing what we're going to do with a silent mind. Are you ready? Here we go. That's about it. So this is what we're going to do in this video. So we may as well get started. All right, so let me start with an example. What are the minima and maxima of the following functions? So first, let me recall that to properly define a function, you need to specify two things, the function itself and its domain. So for my first example, I take the function to be x cubed minus 6x squared, but I restrict the domain to be the closed interval between -1 and 7. So what is the maximum of the function over that domain? So we're looking for the maximal value of the function over the domain. So if I look at the function, I see that its maximal value will be right here at the endpoint. We will call that the absolute max of the function. As for the minimal value of the function over the domain, it will be somewhere like here. So this will be the absolute minimum of the function. But there's also something interesting happening here. So this is not an absolute max in the sense that this is not the maximal value of the function over the whole domain. But if we look at the values of the function near this point, then locally this is a maximal value. So we will call that a local max. All right, for my second example, then I take the function to be the absolute value of x, but I take the domain to be the whole real line. So in this case, if I look for the absolute max, so the maximal value of the function over this domain, there is no answer, right? Because the function will keep increasing forever. So it doesn't have a maximal value, but it does have a minimal value, which will be right here. All right, so let me now formalize the notion of absolute max and min and local max and min mathematically. So let's see the point in the domain of a function f, then f of c is the absolute max of the function in this domain if f of c is greater or equal than f of x for all points x in the domain. And similarly, it's the absolute min if f of c is less or equal than f of x for all x in the domain. So looking back at the examples, what are the absolute max? Well, for the first example, the absolute max here is right at the endpoint because f of c, the value of the function at this point, is greater or equal than the value of the function everywhere else over the interval, the domain. And in the second example, there was no absolute max because the function just kept increasing. As for the absolute min, in the first example, it was somewhere like here, while in the second example, it was here. All right, and we can also formalize what local max and min are. So a local maximum of f of x will be a value f of c such that it's greater or equal than f of x, but only for all x near the point c. And similarly, a local min will be a value f of c which is less or equal than f of x for all x near c. So what does it mean to say x near c? So there's rigorous mathematical definition for that. It means that we're taking all x to be in some open interval that contains c. All right, so looking back at the examples, so let's start with local max. So in the first function here, there is only one local max, which is at this point here. And the reason is that the value of the function here is indeed greater or equal than the value of the function for all x near this point, not all x over the domain. It's not an absolute max, but only over the x near this point. Now, the endpoint here is not a local max. So the endpoints of a closed interval can never be local min and max because they are not included in some open interval because they're the endpoints. Right, so according to the definition, they're never local min or max. All right, and as far as local min are concerned, there are two here in this example. There's this one here, which is a local min because indeed the value of the function is less than the value of the function for all x near c. It turns out that this is also an absolute min. And similarly here, our absolute min is also a local min. With this under our belt, we can ask the question, where can absolute minima and maxima occur in general? So if we look back at our examples, in both examples, the absolute minimum also happened to be a local minimum. So that's the first possibility. Absolute minima and maxima can occur at local minima or maxima. And in our first example, the absolute max was different. It was not a local max. It actually occurred at the endpoint of the interval. So that's a second possibility. If a function is defined over a domain which is a closed interval, then absolute max and min can occur at the endpoints of that interval. And it turns out that these are the only two possibilities. All right, so the second one is pretty easy to figure out. If you have a closed domain, then you can just look at the value of the function at the endpoints. So the first one is the hardest one. So let me now focus on trying to find the local minima and maxima of a function. So how can we characterize local min and max? So let's go back to our examples. So the first one, both the local min and the local max have a very nice property, which is that the tangent line at these points is horizontal. Or in other words, the derivative at these points is 0. Now, this will always be the case when the local min and local max occur at a point where the function is differentiable. And that's easy to convince yourself why. So at these points, well, the function has either a bump or a dip. And at the top or the bottom, then the point will always be such that the tangent line is horizontal. But in the second example, it was slightly different because the local min occur at a point where the function was not differentiable. It was a corner of the function. So that's another possibility. So local min and max can occur where the derivative does not exist. All right, so to formalize that, we'll introduce the idea of critical number of a function. So a critical number of a function f is a number c in the domain, so where the function is defined, such that either the derivative is 0 or the derivative does not exist. And then we have the formal statement, which is sometimes called Fermat's theorem, which says that if f has a local min or max at a point c, then c must be a critical number of f. So in other words, local min and max occur at critical numbers of f. However, the converse is not true. It is not true that all critical numbers are local min and max, right? You can easily find counterexamples. For example, the function looks like this. Well, at some point here, there is a point here which is a critical number because the tangent line is horizontal, but it's not a local min nor a local max because f of c is actually greater or equal than f of x for x less than c, but it is less than f of x for x greater than c. So it's not a local min nor a local max. All right, but if you want to find the local min and max of a function, what you want to do is first find its critical numbers, and then you want to somehow determine whether these critical numbers are local min or max. So we will come back to that in the next lecture. We'll find a method to determine whether critical numbers are local min and max. But for now, let's just stick with this. We know that local min or max can only occur at critical numbers of a function. All right, so let's now focus on the special case where the domain of the function is a closed interval. So in that case, there's a powerful statement about absolute max and min, which is called the extreme value theorem. And in fact, we already used that theorem a number of times in the proof of other theorems. So what is the statement? So if you have a function f that is continuous over a closed interval, then the extreme value theorem says that the function f must have an absolute max and an absolute min somewhere over that interval. It could be at the endpoints. Now, if you think about it, that's a pretty straightforward statement because we're assuming the function is continuous. So there's really only two cases. The function could be constant over the closed interval, in which case all values would be absolute max and min, or it will go up and down, but in a continuous way, such that somewhere in the interval it will take a maximal value and somewhere it will have a minimal value, so it will indeed have an absolute max and min. All right, it's a pretty straightforward statement, but the extreme value theorem is another example of a statement that is relatively obvious, but the proof is very non-trivial. So we will not actually see the proof of that theorem in this class, but we will learn how to use the theorem. So let's go back to examples. So if we go back at our first example, which was defined over a closed interval, then we can check that the function is continuous indeed. So it satisfies the assumption of the extreme value theorem. So then it must have an absolute min and max over the interval, which is true. We've already checked that there was an absolute min, which is here, which is also a local min and a critical number of the function. And there's an absolute max, which is here at the endpoint of the interval. Now, there's two fundamental assumptions in the extreme value theorem, which is that the function must be continuous and it must be defined over a closed interval. If either of these assumptions fail, then the statement of the theorem may not be true. So here's an example here where the function is not actually defined over a closed interval. So I'm taking the function to be 1 over x, and I look at it between the intervals 0 to 5. Then it does not have an absolute max over this interval, because the function will keep increasing forever, so it does not satisfy the statement of the extreme value theorem. but that's fine because the function is actually not defined at 0. So it's not defined over the closed interval here. So another way that it can fail to satisfy the statement of the extreme value theorem is if you have a function that is not continuous. So for example, if I look at the following function between 1 and 5, something like this, then that function is defined over the closed interval between 1 and 5, but it is not continuous, and in fact it does not have an absolute max. So if you look at the function, you would think that there should be an absolute max at 4 here, which is the whole, but it's a whole of the function. The actual value of the function at this point is not 4, it's 3. So the function does not have an absolute max over the interval between 1 and 5. Alright, so we can now put everything that we've seen into practice to find the absolute min and max of a continuous function over a closed interval. So first, by the extreme value theorem, we know that there will always be an absolute min and an absolute max. And we also know that these will be either at the endpoints of the interval or at local min and max, which are at critical numbers of the function. So that gives us a fail-proof method that will always work for a continuous function over a closed interval. So it's a three-step method. First step, you find the critical numbers of the function over the open interval, and you evaluate the function at these critical numbers. Second step, you evaluate the function at the endpoints of the interval. And then you look at all the values, you compare them, and you pick the largest of these values, that gives you the absolute max, and the smallest of the values gives you the absolute min. That will always work as long as you have a function that is continuous and that is defined over a closed interval. So let me now apply this method to find the absolute min and max of our favorite function, which was defined over the interval between -1 and 7. So the first step is to find the critical numbers of the function. So the function here is differentiable, so the only critical numbers will be at the zeros of the derivative. So I calculate the derivative. I get 3x squared minus 12x, which is 3x times x minus 4. And then the zeros here will give me the critical numbers. So there are two critical numbers, which are at x equals to 0 and x equals to 4. Now I need to evaluate the function at these critical numbers. So f of 0 gives me 0. F of 4 will give me 4 cubed minus 6 times 4 squared, which should be minus 32. All right, second step is to evaluate the function at the endpoints. So first, at -1, the value of the function is -1 minus 6, which is minus 7. And at x equals to 7, the function takes value x cubed minus 6 times x squared, which is 49. And then the last step, so by the extreme value theorem, I know that there must be an absolute min and absolute max somewhere over that interval. And I also know that these will be either at the critical numbers or at the endpoints. So I know that one of the 4 values that I just calculated will be the absolute min, and another one will be the absolute max. So all I have to do now is to compare these 4 values and find out which one is maximal and which one is minimal. So I look at the 4 values and I conclude right away that the absolute max will be f of 7, which is 49, which is the maximal value out of these 4 values. And the absolute min will be the smallest of these values, which turns out to be f of 4, which is minus 32. And that's indeed what we've said all along. This is here the absolute min, which is also a local min, and the absolute max is at the endpoint x equals to 7.